Right. Hi, I'm Mike, and today I'm going to be talking about liquid data networking. This is joint work with John Byers. Our work is concentrated on integrating erasure codes into ICN. Erasure code benefits include resilience to packet loss, reduced latency via downloads over multiple interfaces, improved support for mobile clients, improved caching performance. Potential integration overheads include signaling, latency, security, response, and storage. Previous work does not extract the full benefits. Each has issues with at least some of these overheads. Our approach is a network architecture design that provides benefits and minimizes overheads, and also provides a seamless integration into NDN. The LDN focus within ICN is on object to network data name mapping, where an object is a unit of data that is useful. A packet is a unit of data that is transported or cached in the network. And mapping is from object name to packet name. Request response paradigm is how clients and nodes request packets for an object and how nodes respond to requests with packets. Security considerations include an end-to-end object verification and packet verification to prevent denial of service attacks. The NDN approach to these things, you have an object that has a name D. It's partitioned into source packets, and those are given names derived from D, for example, D.0, D.1, and so on. The request response paradigm is that the client explicitly requests all the source packets by name for the object. Security is provided by publishers signing packets and nodes and clients validating signed packets. Clients accept an object if all of its source packets are valid. There's been a lot of good work on integrating erasure codes in ICN. Some of it's shown on this slide here. Of course, there's a lot of other work as well. On the top is shown an object, which is partitioned into K source packets. An erasure code is used to generate additional repair packets, where capital N is the total number of available packets for this object. Coordination strategies are important. An additive response strategy is where the same client receives different packets from different nodes. So as shown on the bottom left, the client is downloading an object from two nodes concurrently, and it's getting purple data from the left node and green data from the right node. And this is important to minimize response overheads because it wants to recreate the object from the minimal amount of data possible. Common response is also very important. This is when different clients receive the same packets from the same node. So for example, on the bottom right, the node is supplying the same green packets to both clients for the same object. And this is important for caching efficiency. And it's also important for signaling and response efficiency, as it sends the request up the stack just once and receives one response back to this node before it provides the responses back to the clients. Prior request strategies include asking for specific data, where a client asks for specific packets of data by name. This is, for example, what NDN does. This does have an issue when a client is asking for packets over multiple interfaces from different nodes. The question is, how do you enable a common response? Random data is a very popular strategy that's used by erasure code approaches. This is when a client requests an amount of data packets and the response is randomly generated encoding data. How to distinguish between common and additive response is a difficult issue here. So in some cases, you want to give a common response and an added response. Further details are discussed in our paper. Useful data is when a client specifies data it has already received, and the response is additional data that will be useful. This, as others have pointed out, has an issue with additive response and also has some signaling overheads. LDN enables coordination through the introduction of the key concept of a SOPI, where SOPI stands for Stream Object Permutation Identifier. A SOPI-P defines a permutation of all the available packets for an object. So as shown below, there's an object D that consists in size of 5 source packets. And for this object, there's n equals 11 packets in total available, and those are shown in a canonical order, ordered 0 through 10. And then in this example, the SOAPy P equals 3.5 identifies a new ordering of these packets, where the new ordering is 3, 3 plus 5 is 8, 5 plus 8 is 2 mod 11, and so on. And this is the ordering of the data in the object stream object d.p. The LDN request response paradigm is that a SOAPy is assigned to each node, and a client requests prefix of stream object associated with the SOAPy. So in particular, in the example below, the client on the left is trying to download a data object D, and it asks for a prefix of the stream object d.p0 from the node on the left that has SOAPy p0, and a prefix of the stream object d.p1 from the node on the right that has SOAPy p1. And if these prefixes are non-overlapping, then this provides the additive response capability. And then the common response is shown on the right, the node on the right on the bottom, where it has assigned SOAPy p1. And both clients are asking for a prefix of the stream object d.p1, and it provides the same response to both. LDN desirable properties are to support large K. Small k forces splintering of objects into many source blocks, which causes large response overheads, which is to be avoided. Support for n bigger than k, in particular n bigger than k squared, is a good choice. This allows minimal prefix overlap of stream objects with different SOAPys. In fact, it can be shown that if you choose the SOAPys randomly, then with very high probability, they will have a very small overlap for the condition above when n is bigger than k squared. And in going further, you can design a large set of SOAPys deterministically that have guaranteed small overlap between their prefixes. And both of these are shown in the reference that's shown on the bottom of this slide. Some erasure code properties that are desirable are linear coding complexity, especially when they're coding repair packets only, because when n is bigger than k, a lot of the packets you're going to be dealing with are repair packets. Erasure code choices include random linear network codes and Reed-Solomon codes. They have significant complexity response overhead trade-offs. The BAT fountain code has OK trade-offs, and the Raptor Q fountain code has near optimal trade-offs. More details can be found in our paper. Here's an example of a network we call the Turkey network, where there's two clients on the bottom, both trying to download the same object D concurrently, each from two nodes. And so these are the requests that are going up. As those requests percolate up towards the publisher, the node in the middle with SOAPy P1 coalesced its request into a single request for the prefix of the stream object D.P1. And then as they go up, the node just below the publisher node has shortened its request. Instead of asking for k/2 from each stream object, it only asks for k/3 because it knows as soon as it gets k back, it can recreate the object and provide the remainder of the responses on its own without any further communication with the publisher. And so what happens is the publisher provides the responses, it lets those go down to the clients, and then as soon as it has k, recreates the object and generates the rest of the responses and provides those down the stack. So at the end of the day, it looks like this, where the clients at the bottom have enough packets to recover the original object, D, and the middle nodes each have k/2 packets cache for D that they can use to provide responses to future client requests. Here's another example of load balancing where the nodes each have an assigned SOAPy and the clients are provided all those SOAPys. So each client requests an equal fraction of the packets it needs to regenerate the object from each of the nodes. So in this example, k/5 from each. And so what this does is it provides automatic load balancing. The requests are equally spread across the nodes in the middle, and it also saves a factor of 5 on storage overhead versus conventional load balancing. This is easy to maintain and transparent to end users. LDN security, we think it's important to distinguish between originator and publisher, where originator is the original generator of an object. It's preferable if this entity is network independent. And a publisher is where the object is available in the network For example, it's the node where the object is injected into the network originally, or the node that generates the object from packets received as the protocols go forward. Object verification is straightforward. Originators sign objects using standard digital signatures. Clients verify objects, and this ensures end-to-end integrity. Packet verification is only slightly more complicated. Publishers verify objects before they generate any packets from them because they want to make sure they're okay. And then publishers, as they generate packets, they sign those packets together with the object credentials. And nodes and clients verify the packets. With this, the misbehaving publishers can be identified and blackballed. In summary, clients are in control. Clients make explicit requests, avoid response overheads. Choosing and assigning SOAPs is an interesting problem. Different SOAPs are assigned to nodes from which the same client downloads is an important design principle. Seems like a small number of SOAPs overall may be possible, TBD. Security, it's important, we think, to make the distinction between originator and publisher. And finally, LDN is an architectural extension of NDN, where the same interest message response protocols can be the same as in NDN. The NDN naming and other features can be directly leveraged, and the benefits of erasure codes achieved and overheads avoided. Thank you.